So for angle of twist, our objective is to show that the cross-section does not change the modulus of rigidity. Okay, so here's the theory. We have our angle of twist equation, which is TL over JG. We are solving for G, which means our equation becomes TL over J phi. J for a solid is equal to pi over 2 times our outer radius to the fourth. J for a tubular is equal to pi over 2 times radius outer to the fourth minus radius inner to the fourth. Okay? Let's say, for example, I have a torque of 0.1 Newton meters. I have an angle of twist of 0.172 radians. Okay, and my specimens both have a length of 400 millimeters. It's the actual length of our specimen. And they both have an outer diameter of 3.2 millimeters. And the tubular one has a wall thickness of 0.8 millimeters. Millimeters. Okay, so that means plugging this into our G equation, we will have, I'm going to do the denominator first because it's bigger, pi over 2 times 3.2 divided by 2, so that gets us our radius to the fourth, minus 3.2 divided by 2, so there's our radius outer, minus the wall thickness, that's our radius inner to the fourth, and this whole thing will be millimeters to the fourth. Our angle of twist is 0.172 radians. And we're going to divide that into our load, 0.1 Newton meters, and our length, 400 millimeters. Radians are considered unitless. I do have my finger quotes up. I've got millimeters to the fourth, millimeters, and Newton meters. So I'm going to go ahead and convert meters to millimeters. 1,000 millimeters per meter. That takes care of you. And that gives me a calculated modulus of rigidity of 24,096 newtons per millimeter squared, which, by the way, is equal to 24.1 gigapascals. Okay? Now you are given 5 different angles with 5 different torques. Okay? So what I'm expecting you to do, ladies and gentlemen, is I would like for you to plot torque in Newton meters to angle of twist in radians. Okay, and by the way, on the results screen, you are going to have radians and degrees. So make sure you're pulling from the radians column. And you're going to have these 5 points here with different values. Okay, I want you to do a best fit line. All right, and you're going to get a slope from this best fit line. The slope we represent as M, and M is rise over run. Okay, so that means we would have this value here from all 5 of our points that we can then plug into our G equation, which will be M, our slope, times L over J, where This is what I mean by M. Okay, so that's what I want you to do. So you should have 2 of these charts. I guess one chart you could put both lines on. Whatever, I'm good. But you'll have one for the tubular and one for the solid. Okay, and what you should find is that they both end up with the same G, because G is a material property, not a geometric one. All right?